Okay, so I think I'm going to start with the permission of the chairman. Okay, so very happy to be here in Alcalá, Henares, giving this talk about the Einstein telescope. I have many slides, but so some of them are going to go very fast, and I didn't want to chop them completely because we'll stay there for the records. I think it's important. Also, I thought it was not a good idea for this audience to go and start talking about the Einstein telescope project, engineering things. So I prefer to put this a little bit in context of what is actually the status of the field in terrestrial interferometry, and then go into what will be the future, and then present the Einstein telescope in that context. Okay, that's made all the talk so long. So I will go very fast on the review of what is the present, and don't look for a comprehensive review of all the results. It's not going to be there. And then I will go into what will be the next. I think in this audience is relevant to know where we go and what you would expect in the next 10 years to come from the results of the experiments. Okay, this you know, all interferometers that now are basically in the equation, LIGO, Virgo. We have a CAGRA already taking data. Advanced LIGO in India is still, I would say, a very preliminary process of construction. Okay, so the fact that we have many, of course, are important to allow precision position in the sky, but also it's important because you need several in order to veto against fake events. And for the stochastic signals, it's impossible to do anything else but correlating different interferometers. So that's the schedule has been revisited essentially, where there was taking a 1 or 2 or 3. All 3 basically finishes last year. And then we are going to go really into next 04. Now we were hoping for December of 2013. Now it's going to be moving essentially a few months. And then we have also a schedule of 5 that will start at a given point in 2026 and then move to mid-2028. I think the message is that there will be a full program all going essentially to the 30s, okay? Another message is that we are increasing the sensitivity, but if you look at CAGRA, the CAGRA sensitivity predicted for the next run is very marginal, which means that we are not going to have this capacity of pointing that everybody would like to have. And this is very relevant for electromagnetic counterparts. Okay, that's what we have. It's about 90 events of all possible kinds. And you see the progression, you see that. And the reach in distance that we have actually reached for neutron start. So this is just very fast to tell you that with these statistics you start looking at populations in terms of total mass, ratios, you start looking at the spin configurations, how they look like, and then the bottom line is that you have you have symmetric but also very asymmetric configurations. You have indication of its orbital speed precession, and these all points to different possible mechanisms for the binaries. But what you don't have is a very precise scale location, because this is basically you need more and more interferometers to narrow down this. Okay, you do more population studies, and basically now we start seeing that there are peaks in mass, and we start measuring the rate of mergers versus redshift all the way to about 1.5 in redshift. All of this is consistent with the star evolution, but this is the data, and this is basically prediction for the star formation, and essentially to the level that we can say is all consistent with models for the star evolution. Okay, we have events that have been discussed like this, with very heavy masses, which are basically in the mass gap, and this start challenging stellar evolution models, but essentially people start thinking in terms of this kind of hierarchy evolution that you have several mergers going into a big black hole. Okay, that's basically what it is. The party line is pretty much that we have seen a history of mergers. And then we do tests of general relativity in different ways. We can check the speed of the gravitational wave. We can check the depends of the frequency with this speed, so there's no dispersion. We look at the polarization, and we can even expect very carefully the evolution of the phase. And when you do that, you do a Taylor expansion with all the post-Newtonian terms. And bottom line is that basically you try to modify the waveform, but essentially the data is telling you these modifications are consistent with zero, and all this is consistent with GR. You do more things. You do something which is you split the waveform in two. You expect the spiral part, and then you expect the rest to see whether everything is consistent. The bottom line here is that in order to do the test of GR, you inject GR to extract the signal. So there is a little bit of logical. So you try to at least split the signal in two and see that everything is consistent. So the masses and the spins taken from half of the waveform or the other half should be consistent, and everything should be, you made these things should be zero, and well, the things are basically coming. I show this because then I will show what happens with ET when you start doing these things. Then you know this very well, and then this is basically you can check the speed of gravity by this multi-measured event, kilonova. You know this also very well, that then you can, if you find, you know the redshift, you know the distance, and you know the velocity, then you can extract the Hubble constant. And this is a value that is just extracted out of one event, okay? And we were hoping to get much more of them. Unfortunately, this is the only one we got, which tells you that probably we were very lucky. But okay, that's basically what it is. And then you know this better than me. I will not go for that. Basically, this is zero. Then one thing that is done, and this you know, is that we look at the tidal effects on the waveforms in order to see two things: whether we could see them, and also to discriminate between is a neutron star or is a black hole. We inject these modifications into the structure of the signal, and if you don't see really the effects, then it's more like you have actually a black hole. And clearly, this is you are the experts on that. You go into high density, low temperature, and you can study the neutron star equation of a state. Okay, so this has been done with this famous event, and this is the results from LIGO Virgo, where you just look at the formality, radius versus mass with different families of some of you are from you, and then there is the power to start excluding some equation of a state that predict less compact objects. Okay, that's point one event. Then what is the future? The future is that if you look at the expected improving sensitivity, you will get a factor of 3. I mean, typically goes like the volume. So you have a factor of 3 more data in 04, factor of 5 in 05. So by the end of, by 2028, you will have all the 2,000 events. Okay, so we are going to be reaching the point where we saturate. So in the last 5 years, we are going to saturate the design sensitivity. There are some ongoing discussions on how to extend the life of these interferometers, and this is what I'm going to talk to you now about. But then it's the time to start thinking about 3G. So this is basically the thing. Now, when you finish 05, at any point 2028, this is an old plot. This has been shifted basically due to COVID a little bit.
Question. Yeah. What is 1G, what's 2G, and 3G?
Sorry, this is too much jargon. It's second generation, third generation.
Is there a first generation?
Yeah, first generation was supposed to be the original LIGO, was the very first generation, without frequency-dependent squeezing integration. But okay, it's basically, sorry, I say too much jargon. I should spell it out. So basically, there is a discussion of what we are going to do after the program now, and I think probably we will extend the program, okay, before talking about new facilities. That will happen. What is going to sell this? Okay, there's a way to do this. Okay, there are different ways to do this. More power in the laser, larger test masses, better coatings in the mirrors, better quantum squeezing, and so on and so forth. But what you are, for this community, what is relevant is to tell you that you are going to get a factor of 2 in sensitivity, factor of 10 in rates, factor of 3, the order of 3 kilo events. Kilo euros would be good, actually. Kilo events in 1 year, and reaching binary neutron star up to the 600 megaparsecs. I think for this community is only one. But also there is one message. After we do this, we enter in what the economists talk diminishing returns. So then you want to move more, you need to run for a long time. That's diminishing returns. And then at a given point, you need to jump in technology. Okay, so there is a program in US, which is basically post-05 as well. I will not go into this, but basically this is the program, what happened after 05. But then what happened later? What happened later is the third generation. And the third generation is ET and other things. So let me show you that. So things that happens in Australia is that NEMO is called. So you do an interferometer, focus on very high frequencies. So precisely when you want to study of high density, low temperature. Okay, but you focus on the high frequency where all the post-merging physics happens. And therefore is where you want to study the modes of the neutron stars, right? And then, okay, that's basically what it is. This is in discussion. Then in US, there is the program called Cosmic Explorer, which is essentially right now taking momentum, although has still in, I would say, earlier stage compared to ET, but time will tell. US can be very fast if they want to be fast. So at the moment, the budget is 1.6 billion American billion. So it's about 1.6 thousand million euros, so dollars. And what they want to do, or they put forward to do, but things will change, of course, is that to simply extend a factor of 10 LIGO. So do a factor of 10 LIGO, 40 kilometers of 10, complemented with a second one with 20 kilometers. One is multi-purpose, the other one is, okay, is providing, let's say, the complementarity to the 40 kilometers, but also is focused on neutron star post-merging, and also is allow you to measure polarizations and information, as it happens now. Okay, these are details that talk to whether to use post-05 Voyager technology, yes or no, but I think the bottom line is that at the moment, US is simply starting the process, and the first idea forward is to simply extend factor of 10 LIGO. Where? We don't know. Okay, so there's a lot of good words by US. I mean, there is different places in US where the project start getting momentum. But let's go into Einstein telescope project. That's the European version. So this version is in the current design is a 10 kilometers triangle. On the ground, we updated the conceptual design in 2020. The original was like 10 years before. And what we did was to essentially submit this. Okay, let me go into this, 2G to 3G. So instead of going for Virgo, it's 3 kilometers, like with 4 kilometers. Instead of going for 3-4 kilometers, you go for 10. Instead of doing the classical L, you start thinking very fancy of doing multiple interferometers put on top of each other. So basically, you have a triangle of 10 kilometers. In each of them, you have an interferometer which is 60 degrees, as you see. It's not 90 degrees. And then you put 3 on top. And on top of that, each of them is actually twice, because you go with different lasers to go low frequency, high frequency. Okay, that was the original proposal. Has a lot of goodness. You can measure polarization yourself. You can intercalibrate yourself, but also you can do in a way that you remove basically you put these interferometers in a mode that essentially you should not see any gravitational wave, and therefore you can really define very well your noise and redundancy and so on and so forth. And okay, that's the original thing. It's very complicated. Why you do this? Why you do all these things? As I said, is on top of that there are 2 in 1. So you have one at high frequency, one at low frequency. So it's 6 in 1. and we call it xylophone. Okay, the idea is that if you want to push in low frequency and you want to push in high frequency and you want to do it in the same interferometer, you cannot do it because you need, for high frequency, you need high power. For low frequency, you need the things to be quiet. So you can have to go even higher. So the way to do is to really split. Split basically in two lines. Okay? And then when you put all together, you do the best in all overall. Basically. Okay, so this is basically to say you do two, and then you do one around temperature. This is the LIGO Virgo plus plus. It's brute force. It's basically more power, larger mirrors, longer, etc. This is more like pushing the low frequency, and then means that you need to go cryogenics. You need to change the wavelength. This talks to the mirrors. The mirrors should be transparent to the wavelength. So, and then you have to change the technology. And then you need to go into a lot of R&D to understand how you do all this. These, more or less, you know how to do it. Okay? There are some challenges in terms of putting more power, but in principle, you know how to do it. Okay, so there's a lot of R&D. R&D on new attenuations, new optics, new materials, new coatings, new lasers, etc., etc., etc. And this all to reach really the 10 to the minus 1 precision. I just put here some. This is kind of a publicity slide. But basically, this is basically all you need. Okay, so there are R&D platforms already taking place. There is one in Maastricht, which is, this exists. I should put a picture now. It's a huge clean room. All the building is a clean room, where you have a small interferometer. This is 10 meters. Instead of 110 kilometers, 10 meters. But the idea is that you develop all the technology on cryo suspension in the towers. Okay, so there is similar things are happening in Rome these days, and there is a lot of work to be done to grow very big mirrors with very little defects, and also you need to work on coatings in order to cope with all this power. Okay, so all this kind of R&D is happening. Okay, so this is just to say how it looks like. This is what could be put at LIGO Plus is basically the design of the second generation, potential second plus, and then the third generation. You see, and this is NEMO. So NEMO goes to high frequencies, and all the rest is really a way to broadband. Now you notice that the broadband the fact that Comic Explorer is better in the center is because you go 40 kilometers. Okay, it's basically the distance. But the fact that Comic ET wants to go low frequency, and this is where you have to go cryo and so on. Now, why you want to go such low frequency? Well, because if you look at this is a significance of the signal versus the time to the mergers. Okay, so basically it's a way to say you are sitting there, and in the case of LIGO, you see the event only 0.1 second before the merger happens somehow. Okay? Because you don't have the sensitivity to see it. But if you go to ET, you will see things happening 3 hours before. So 3 hours before you know that something is happening, you can talk to everybody and say, in 3 hours you're going to have a collision, a big thing. So put your telescopes there. Okay? So that's why things want to go pushing into the low frequency, because you are seeing more and more and more of the spiral part. Okay, that's basically the bottom line. Okay, so this is also a publicity plot where you simply see, you compare the second generation, goes to Z of 2, I show you a plot up to 1.5. If you go to third generation, you go to redshift of 100. This is in the dark age. So there are many things that you can do, like looking for collisions here of black holes. If they happen, they need to be primordial, absolutely, there's no way. And then you can do cosmology, because you can follow all what happened all the way to, with many, many, many decades in time, okay? One important thing is that if you are so good, then in selecting the events, you are very, very clean, then you can do very, very precise tests of general relativity. I will say something about it. Okay, the numbers you want to know is this, is the prospect as basically 10 to the 6 black hole per year, up to redshift of 20, 10 to the 5th, 10 to the 5 neutron star, up to redshift of 2, and order 10 to the 2 to 10 to the 3 events with electromagnetic counterparts. Order. Okay? So basically, you see there are 2 orders of magnitude you lose because you need to be lucky in order to be basically well pointing and so on and so on. Okay, so you can do all you can imagine here. Probability neutron stars is very well here. One thing that you can do is this plot. Is that you can look at the merger rate. I show you a plot all the way to 1.5. Now you go all to 40, you can see whether you have population 3 stars, but also whether you have primordial, because if you start seeing a population that a merging rate that goes with redshift, it's clear it's primordial. So this plot already has a lot of information. Okay, sky location, important. ET alone will allow to see more than 10 events per year with a scale location which is not very good. It's actually 100 square degrees. If you combine the network, so ET plus 2 cosmic explorers, then you will have 1,000 events, and then the location will be about 1 degree, which is not small, but clearly it's much better than the 100 per degree. So it's clear that you need the network. It's not a competition between cosmic explorer and ET, it's actually that we need to have them. This is just to show you, of course. The timeline of ET is similar to the timeline of many of these things, so there will be a lot of multi-messenger. Okay, so general relativity, and you can do many things. Let me show you basically this plot. This is what happened in LIGO, the yellow, and this is what happened in Cosmic Explorer. ET will be the same. So you see that you now understand why I said that you can really go through very detailed events. So you can do very big tests of general relativity, and you start doing this thing I show you of splitting the event in 2, then you can, instead of making deviation within 20 to 30%, you can see deviation within, or basically 1.1%. Okay? So you're going to start really testing general relativity well. Now, I was talking over the lunch. This is assuming that you are isolated in the universe, nobody else bothers you. If you are in the middle of some environment, you need to take into account environmental effects. And clearly things will be spoiled a little bit. Things you need to understand. You need to do cosmology. Clearly the cosmology will introduce deviations between redshift, distance, and the Hubble constant, which is not the Hubble constant anymore. If you go cosmology, it really, you include all the densities. Okay, and in principle you can do, you can test many fancy models. And for that you need a few hundreds of binary neutron stars. Okay, and then cosmology, I will just skip this thing. The only thing is that cosmology, you do early universe, the gravitational waves are the only thing that go back of the CMB. If you do third generation, you are talking about very high frequencies, which means immediately very high temperatures. So you are doing physics at the universe at very high temperatures. Okay. Now let me talk about ET in a different way. This is ET politics, okay? So let me just show you. So since we are in Spain, let's say what happened in Spain. One slide, I promise, nothing else. So we have, back in 2020, we start thinking about that we should organize ourselves. So we organize ourselves in a meeting to prepare the ET proposal to Europe. There was the moment where ET wanted to be declared as free. And this means that the ministry needs to send a letter to Brussels saying we are interested in this. And for that, they need to see the community. So we did that. We organized ourselves. There was a big, large number of institutions interested. And then based on that, and based on the documents that we sent, then Spain politically supported ET. This is the map of politically supports that we have at the time of submission for S3. And then back last year, already 1 year ago, Einstein was included in the roadmap. Now, once you are included in the roadmap, you need to talk about, okay, now it's time to get serious about the project, okay? So basically we got approved, and then we have a long way to start preparing the experiment, all the way to physics. Now, when is going physics happening? Okay, 2035, something like this, like in 10, maybe 15 years from now, okay? But we have a lot of things to do. We need to R&D and do the technologies. We need to decide where we are going to build it. We need to decide what it's going to cost, how we manage ourselves, how we get the money, etc., etc., etc. Okay? Okay, so we are entering now in what is called the preparatory phase. Okay, there we go. So this is one project that is European project for preparatory phase, which has to do with all these things, was approved. We manage it in Spain. And these are all the countries that actually got it on board. Okay, and you see, compared to the previous map, clearly now we are growing. Okay? Basically, everybody is there, and we hope that we can get a few other friends. But basically, big Central Europe is there. Okay, and these are basically the same thing. This is just to tell you how we organize ourselves. But I want to say two things. One is that, well, we are, as Spain, coordinating it, but also we have CERN on board. CERN is not going to build ET, but they are very interested in running some of the aspects. So CERN is on board. Also, we have the Supercomputer Center on board. Also, we have the Ministry Industrial Returns Agency on board. So I think we are doing well. Anyway, so this is basically, we are organizing the collaboration, we are organizing the observatory. ET will happen what happened in LIGO and in other observatories, which is going to be an observatory, and then you have a scientific collaboration. So there will be an organization to build the experiment, and there will be the organization to exploit scientific experiment. And that's basically what is here. The ET collaboration and the ET directorate, okay? And then what is called ET Observatory. And we are organizing this. We are following very much CERN model in terms of council, everything. Basically, we are very much inspired by CERN. Many of the people that you see here, we were very close, so we are very close to CERN, and that's basic. And what I was saying about CERN, CERN took the responsibility to design the vacuum pipe, okay? The vacuum pipe of ET. I will come back to this. I have 1 minute, I guess. So where we are going to do it? Well, we don't know. But the thing is that there are 3 potential locations in the market right now. One is in Limburg, one in Italy, in Sardinia, and one coming in Germany, in the area of Saxony. Okay? So these things were clearly declared themselves as seriously competitors. Germany is doing prospects in that area to see whether here they could build eventually ET. So I would say there are 3 signs on how putting forward. Okay, this is just for those of you Germans, this is just to tell you, you know this about it, that there is the idea of building a center in Saxony where one of the pillars of this center is to really see whether we could build ET there. Anyway, so what is the cost of this? And I think I'm going to. So the cost of this is about 2 billion, 1.9, similar to what US says the economic affair will cost, about 10 years. And I think it's very important to show you this because the experiment is 2 billion, but the amount of work that you need to put in optics and laser and money, you know, is this that this? It's just basically 10%, let's say. Most of the cost is actually digging the tunnel, making the vacuum system and cryogenics, and that's why now I tell you that's very, so relevant that CERN took responsibility of the design, because it's 1/3 of the cost. 1/3 of the cost is actually the design of, building the thing, and you have CERN building the LSC going to design for you with help. The vacuum pipe and the cryogenics is actually good. Now, it is expected that the country that want to host it, it will pull forward basically 50% of the money. Okay, as usual. Okay, so what is the money? Okay, so as I told you, there are 2 which are more, and the third one which will come up and surprise us. I'm sure it's going to happen. That essentially, Netherlands, in the formally requested, I should put in past, about 1 billion for ET, and was approved. Actually, ET, the government of Netherlands put on the table almost 1 billion. Now, out of this, 50K, 50 million is for you go and you do R&D. The 850 million we put in the pocket, and the thing comes to here, then I put out the pocket. but it's really allocated and it's there, the money's there. So Italy is doing more or less the same thing. They were doing it in the same way. Now Italy has elections this weekend, so we'll see what happens. But they got already 50 million. So the R&D equivalent brought the money they got. Okay, of course, this is a kind of a slide you prepare for funding agencies. So clearly, when you see this, Spain needs to start moving basically with the chairs. You need to do something. Okay, but basically, having half of the money already allocated and secure is something very important. Okay, one example, I will finish. One example is the vacuum pipe. As you said, it's 1/3 of the cost. We need to design this. It's a lot of money, a lot of work, and this is a place where people can contribute a lot, and you don't need to know about interferometers. It's really pure mechanics. And this is the collaboration formed in June of this year, formally formed. This is how the collaboration looks like now with different countries. Surprise, surprise, Italy actually is 1/3 of it. Basically is what it is, always the same thing. So I finished, okay? So I will not sell you the field. I think it's clear that we don't need that. The project it is a leading 3G project in the world. It's clearly the European one. We are very well advanced. We are in the position, we means here in Spain, that we coordinate the preparatory phase, and no doubt that there is enormous synergies with nuclear and particle physics, but also there are huge opportunities in terms of industrial returns and to society, but in principle industrial returns on things that I think many countries, but also Spain, can play very hard on this. Okay, and I think this is all I have.
All right, thank you very much. Questions, please? I'll break it what people think. I was asking myself what the site characterization board is doing inside the scientific collaboration. Yeah, because site characterization is something that can at the beginning be part of construction and later be externalized.
It is. The collaboration has a group of people that work on this, certainly, but during the preparatory phase, we have a working group in the preparatory phase project that with a mandate to put ourselves in the position that we can do a frank and honest comparison between the information from different sites.
Right, but it's in the scientific collaboration, it's not in the construction structure.
The science is in the exactly, yeah.
So it's very curious.
Why? Well, because you need to characterize how this affects the sensitivity of your interferometer. In order to translate everything into sensitivity of interferometer, you need to have all the inputs from the scientific community on how you compute the sensitivity. Okay, that's one thing, but let me say that next to the other of that, there is one part which is civil engineering, which also talks to geology, which is part of the project. So it's not only whether your soil is good enough to do the experiment, it's whether we can actually dig the cavern. So it's both things, if you wish.
More questions?
What's the schedule of the site selection?
Okay, that's a good question. What we promise,
Can you
what
repeat
we
the
promise
question?
is that would happen within the preparatory phase. Actually, we promised 2025, but this is 1 year before. But we didn't put in stone in a way that you don't want to somehow put yourself, you have to contradict yourself. But I think the statement that the governments will not affect if we finish the preparatory phase, 2026, but we didn't decide what the design is. Basically, so 2025 on the paper, hopefully we do 2025, but for sure we need to finish the project of the preparatory phase with that decided, otherwise everything starts evaporating.
Anybody else? I'll ask another. Where is the project short? What is needed?
Okay. you know. What is needed apart from money?
Well, it seems like the money is flowing.
No, because...
Promise, at least.
You know, we need to find 1 billion. It's clear that if Italy finds another billion, it's not, you don't have 2 billion. It goes to Italy, Italy goes 1 billion, otherwise it's 0. So you need to find €1 billion anyway. And, but in terms of technology-wise, what is needed? Okay, so I think there is a lot of work to be done on R&D for mirrors, for stable lasers, for squeezing. But let me put one example which is much simpler than that. We are going to build 120 kilometers of tube. We need to decide how we do it, how wide we do it, with what material we do it, how we instrument it inside, because if you shoot a laser from here to 10 kilometers, I guarantee you that you don't find the laser after 10 kilometers. So you have to find a way to see how I pre-align all these things are things that are accessible to us. I mean, you're talking about we need to do R&D on coding, optical codings. There are very few companies in the world, maybe only one in France, that can do it. But we are talking about other things. Many people can jump into the game.
Thank you very much, sir.